I'm doing this example because it is the smallest example I could dream up that shows all the things, or almost all the things, you're going to do in this class. Essentially, when we do control, the way we do it is this. We have something that we want to control. And in our case here, we have an RC circuit. Notice the picture on the screen. You see the resistor and the capacitor. So when you hook this circuit up to an input voltage, make Vn, say it jumps from 0 to 1, then the current in the resistor starts flowing because you can't change the voltage on the capacitor instantly, and not unless you have an infinite voltage or infinite current source. So essentially, what happens is that the capacitor slowly charges up. And it gets slower and slower and slower the closer it gets to being fully charged. So essentially what we're going to do is we're going to try and make this capacitor charge up more quickly. Instead of going as e to the minus t over rc, which is the way it naturally charges up or discharges, we're going to make it go as e to the minus 10t over rc. And so the eigenvalue, or the pole, or the root of the characteristic equation that you guys learned about when you were learning about linear systems before, that is going to be changed using a thing called state feedback. We're going to change it from e to the minus t over rc kind of solution to e to the minus 10t over rc. So it's going to go 10 times as fast. So how do we do that? Well, here is my little circuit right here. This is the resistor, and this is the capacitor. And I have here a controller. What I'm using is the same controller that you guys will be using. This is an ESP32 microcontroller, and it's connected to my PC via USB. That's what's powering the whole thing. And this microcontroller has on it two useful things for this control project. One of them is called a digital to analog converter, or DAC for short. That digital to analog converter will put out a voltage, and that voltage we will use to drive this RC circuit. It's the yellow wire here and the black wire. Together, that's making that voltage. That is the Vin voltage on the green and blue picture of the schematic of the RC circuit. So we're going to drive it with the digital to analog converter. And then the other thing this MSP32 has, or ESP32 has, is an analog to digital converter. And as you might imagine, that takes the analog voltage. In this case, I'm hooking up to the output voltage, or the capacitor voltage, and it measures that. It actually converts that voltage into a digital number in the computer. And you can use that number then to do some mathematical calculations, which we'll do inside the computer here. We'll show you how to do that in the software. And then that uses those calculations to figure out what to put on the input voltage here to make it charge up more quickly. So essentially what it's doing is it's watching the output, and based on what it sees on the output, that's the capacitor voltage, which is the state variable in this situation, it measures the state variable, and then based on that state variable and previous calculations, it multiplies that state variable by a number that we calculated, and that makes the voltage that goes on the input here to make it charge up 10 times faster. So when I'm doing these kind of projects, it's very important for me to keep notes and to do documentation, because really engineers are paid for doing documentation. They're not paid for making fun little toys. They are paid for making the process that other people can use to build hundreds of these, or you know, whatever. Or even just to figure out the process so that somebody else can do it. So what we're doing, we need to document. And I'm using a thing called IPython notebooks. I like them because you can write You can have pictures. So that's how I got that schematic. Sometimes I need to use equations. Engineers use a lot of mathematics. We're using a lot of mathematics in this class, and so it very nicely makes it so I can write equations. It uses a format called LaTeX, and that's something you should probably get familiar with if you're not already. So you can edit these equations, you can write text, you can put pictures in there, and then besides that, it allows you to put code. And the reason this is important is because when we're building a system like this, we need to actually do calculations, really numerical calculations. You know, symbolic formulas are nice, but we really need numbers. And it's very nice to simulate how this thing might behave before you actually build it, because you can find problems that you weren't expecting, and having it in two forms. One is your computer and the other is the actual thing. You can compare these two forms, and it's kind of like gives you an advantage in that if one of them says something and the other one says something else, you know there's probably a mistake in one or the other. And so it will help you find your mistakes if you make it in only one platform or not on the other one. So basically what I did here in the previous part of this notebook was I wrote the schematic of the circuit, and here I came up with the state equations for the circuit. You see VC equals minus 1 over RC times VC plus 1 over RC times Vn, and this first minus 1 over RC is the A matrix, and the second 1 over RC is the B matrix. You know, the A matrix is a negative 1 over RC. So anyway, you can see all that. I wrote all that down, and now I've got this Python program that is supposed to simulate this circuit. So in order to do that, you just click in what they call the cell, which is you know, this section. You see this little blue line here, this section, and the code is kind of highlighted there. And you can hit Shift Enter, and then it actually comes out with this nice graph. And you see it's going as e to the minus t over RC there. That's the capacitor voltage. And it tells you what the eigenvalue is because I ask it to. The next section, I'm using a thing called state feedback to determine how much I want to drive this input voltage here with the DAC. And essentially what we're doing is we're measuring the capacitor voltage, and based on that, I multiply that voltage by a factor of, I think it is 9, and then I subtract it out from whatever was going in there before, and that's what the new thing looks like. I would like to make a couple comments about the nonlinearities of this microcontroller. So the microcontroller is actually the most nonlinear part of this whole setup here. The circuit is quite linear. In other words, if I double the input voltage, it'll double the capacitor voltage and all that, and double all the other things that I have in the circuit, more or less, until maybe if you got up to some enormous voltage, it might burn the whole thing up. But in general, it's very good that way. However, the microcontroller here is running on 3.3 volts. So what does that mean? That means when you ask the microcontroller to put out a voltage of 5 volts or 10 volts, it can't. It can only go between 0 and 3.3 volts. So the digital to analog converter is basically limited to the range between 0 and 3.3 volts. What I've done here to try and make that, get around that little problem, is I've tried to center our voltage that we can use, 0 and 3.3 volts. Actually, I'm trying to center my quotes ground or 0 right in the middle of that. So instead of calling you know, C level at 0 volts, we're going to count C level at 3.3 volts over 2. And the analog to digital converter is exactly the same way as the digital analog converter. It can only measure voltages between 0 and 3.3 volts. So we have to make sure that all of our voltages that we're feeding this thing and that we're reading from it are in the range of 0 to 3.3 volts. So that probably made that was maybe the most challenging thing about this little demo. And you will probably find that your project also has some challenges based on approximations you wanted to make or linearizations you had to make. In this case, I'm making a linearization of this circuit about 3.3 volts over 2. And so that's my what we call Q point. So now let's go and show you how we would actually develop this thing and make it work. So remember, we were using 6302 view. So in 6302 view, we actually program this ESP32 using the Arduino development environment. You know, you can use VS Code or some other development environment if you prefer, but the Arduino one is probably the simplest one, and it's the one I'm going to demonstrate here because a lot of you will probably be wanting to do this the easiest possible way, at least to start with. So essentially, what we have in this code here is I have taken an example off of the 6302 view website, the GitHub website where we pointed you to and you downloaded that code for your computer. And I just took one of their examples. I did what they said there. I moved the 6302 directory into my libraries directory for the Arduino IDE, as I showed you in the previous video. And that actually, you know, made it so if I went over here to File and I did Example, and if I go down here to the libraries, it might help if I got my glasses on here. Yeah, there it is, 6302 view, and here are 3 examples that you could start with. So essentially, I just started with one of these. I think I started with the square and the serial one. Now, the serial one is because in my example, I'm connecting via serial through this USB cable right here. And then in this 6302 software, there are 2 important things. The step time, which I have as 10,000 here. So what does that mean? That means every 10,000 microseconds, we are going to make another measurement of the capacitor voltage, and we are going to make another measurement or put out another new voltage into the input. So every 1/100th of a second, or 10,000 microseconds, it's going to do that. And the second thing, the report time you see here, is the time between points that will graph on the GUI which I'm about to show you here. And then basically you go follow their example, you can read their document page, and it will help you. Essentially what you do is in the setup function you add all these things that you want, like if I want a slider or a graph or whatever on the GUI, then you add those in here, and then in your loop function you basically do whatever you want to do with those things every 10,000th of a second, and then down at the bottom of your loop you have this cm.step. So basically it does all your stuff in the loop and then it goes off to cm.step. So while that 1/10,000th of a second is happening, or what is it, that 1/100th of a second is happening, the 6302 view is sending data from the microprocessor back to your computer. So in order to compile and build this thing, you use this little right arrow here. You click on that, and it starts compiling the software here. You can see it's compiling the sketch here, as it says. And then hopefully there's no errors. Looks like it was no errors. And now it's uploading, and you can see how many % done it is. And now it's uploaded. So then the next step, now that we've loaded this software, it's running on the microcontroller, we're going to go to our terminal here, and we're going to start the Python script. And the way you want to start the Python script, well, let's see, here it is. It's Python 3. That's because we're using the 3 version of Python. And then you need to be in the directory, the GUI directory of the 6302 software that you downloaded. So you say Python 3, and in that directory there's a local server.py file. And so you do /localserver.py. The / really means just use the localserver.py that's in this directory. And then if you wanted some help on this thing, you could go --help or -w, and -w uses a wizard, and it actually asks you the question, you answer the things. But for me, I got tired of that, so I just do -d3. So what does that mean? The -d3 tells it I'm using an ESP32 processor, and that way I don't have to answer all the questions. So I'm just going to hit enter here, and now you'll see it start printing some stuff, and it'll say serial connected. So it does that, and if it doesn't say serial connected, you probably haven't done this part of the thing. And the next part is you go to your folder where the local server is. There's also a file called GUI.html, and you double click on that and it opens it in your browser. And I've already got mine open over here in the browser, and it looks like this. And now you can actually see what's going on this thing once you hit reconnect or connect. So here we go. So I'm connected now. And you can see the voltage right now. What I'm doing in this case is when I charge up without any feedback. So this is just charging up e to the minus t over RC. And if you want to, you can actually make this thing zoom in and out on the graph. If it's going by too fast for you, you could zoom out like this. And you know, if it's going too high, you can go like this, zoom out so you can see the whole thing. And right now it's charging up as e to the minus t over RC. And this thing actually, I've forgotten how long RC was, but it was probably, you know, something like 10 seconds or more. It's taking a while. Maybe it was 30 seconds. So every 30 seconds, what I do is I charge it up for 30 seconds, and then I discharge it. And if you notice, you will find that this thing is actually dropping 10 times faster than it charged up, because I have the feedback on over here on this little slider. And you can look at the software and see how I added this little toggle switch, how I added these things right here. This tells me the U value. This is a number between 0 and 255, which is basically the digital analog converter value. And this is the number of microseconds that's passed. And over here you can see when I changed U. I changed U at the points where you see the inflection in the curves down here on the capacitor voltage. So right now I'm trying to charge it up, and when it gets charged up, then I'll have it discharge. And on this one you can see it discharging quite quickly, and that's what we desired. So in essence, what I'm saying is the 6302 view is a very useful tool for you. And it entails several things: the Arduino programming environment, the Python server. You know, you've got to hook up your actual hardware there. This little example project here will give you a little bit of a start on your project, which will be essentially the same, except that instead of one state variable, you'll have either 2 or 4, you know, more state variables to control.